So I try to group papers into groups, and this first session is perhaps some newer methodologies that I think a lot of people across different areas of social science are interested in. And our first speaker is Colin and Peritz, and we ask the speakers to talk for 25 minutes and leave 5 minutes for discussion.
So, did you all
Yes,
do
okay,
the
so yeah.
presentations?
Yeah, so she's just in control. Further down. Okay, and there's a click here.
Great, thank you.
And point.
Okay, hopefully not too technical. All right, well, thank you so much for inviting me to participate in this conference. I'm delighted to be able to present some ongoing work. The project here is entitled Do Preferential Trade Agreements Increase Trade? And I use some network analysis, statistical models to try to get at this question. Let me begin with some current events to help motivate the project. As most of you are probably aware, the Trans-Pacific Partnership is a multilateral trade agreement negotiated among 12 different countries, including the US, Japan, Korea, and a number of others. And the Obama administration had been a major proponent and as a way to expand trade with numerous Asian and Pacific partners, and to lock in trade rules that would be strategically favorable to the United States going forward. One of the many justifications has been to secure favorable trade relations with partners that might otherwise be drawn to China. However, the Obama administration, despite having negotiated for several years and arrived at a highly detailed multilateral treaty, encountered resistance at the ratification stage. Dissent in Congress meant that the trade agreement did not go up for a vote before the 2016 election. And then one of the first moves of the new Trump administration was to withdraw the US from the Trans-Pacific Partnership entirely. Among other reasons, the Trump administration argued that the TPP would do little to expand exports to the US, from the US to foreign markets, rather leading to an import surge. On both sides of the aisle, there seems to be this assumption that trade agreements, such as the TPP, have a very large aggregate effect on trade flows, and both suggest that the effect would apply not only to members of the trade agreement, but also to non-members, for example, by excluding China, which was not involved in the negotiations. So preferential trade agreements are treaties that governments sign in order to set terms of international trade. They typically grant each other preferential treatment, meaning more favorable market access. A familiar example is the North American Free Trade Area, NAFTA, which eliminates tariffs and quantitative restrictions, for the most part, for the US, Canada, and Mexico, while allowing each country to independently set their trade policies for non-members. Notably, these trade agreements can take different forms, and some being more stringent than others. Almost all countries are part of at least one preferential trade agreement. And the data I use in this study accounts for approximately 200 reciprocal agreements currently in force and many others that have been in force over the past few decades. Because some countries may have overlapping commitments, it's informative to think of them as forming a network. So the substantive questions that I'm interested in, first, when do countries form preferential trade agreements? You can think of an example. The US has a free trade agreement with Korea and a separate one with Australia. At the same time, Korea and Australia have trade agreements with each other. And so when Korea sets its trade policy, it's beholden to both its separate commitments to the US and to Australia. And so does that incentivize different trade agreements to be formed? Certainly there are approximate reasons. Governments may wish to enhance trade with other members of preferential trade agreements, but there's also anecdotal evidence for secondhand effects or externalities. When South American countries negotiated Mercosur, for instance, they banded together to gain leverage or bargaining power when interacting with the North American members of the free trade area. In other words, one PTA may beget another. The second related question is, do preferential trade agreements actually promote trade? And it's important to distinguish between expansion of trade dependence, which may bring efficiency gains, and trade diversion. If preferential trade agreements simply redirect trade from one partner to another, there may be little economic payoff for negotiating these complicated legal contracts. And this has been a point of contention as the European Union expands. To give you a sense of the scale of the trade agreement network, let me illustrate some snapshots in its evolution. This figure shows trade agreements formed between 1966 and 1970. Most of the activity was regionally focused, including, as you can see, the predecessor to the African Union. The activity intensified in subsequent years with expansion of multilateral agreements. And in 1991 to 5, we see significant expansion of the European Union membership, for instance. And so what I'm doing here is treating each country as a node and the trade agreements as ties or edges between those nodes. More recently, preferential trade agreements have been formed cross-regionally, as is evident in the illustration of PTAs formed between 2001 and 5. So that's more recent. Okay, so as you've probably gathered, the number of preferential trade agreements in force has substantially grown over recent decades, and this effort towards legalization has not been limited to any particular countries. Rather, the number of countries that are members to at least one PTA has steadily grown to the point that nearly every country participates in this network. As countries have more trade agreements, we can think of each country as a node, the trade agreements as a tie or edge, as I mentioned, and the density statistic as an informative measure. This network has become more dense over time, particularly since the 1990s. So lots of work on international politics uses descriptive network statistics, as I've shown so far. But to really get a hold on the mechanisms I'm interested in, I want to do something inferential. And so to figure out how trade and PTA formation is related, we need to account for the important indirect effects of the network structure and the indirect effects of trade diversion, and so forth. In the political science department here at Davis, Professors Maus and Kinney have been very innovative in building and applying inferential network analysis to political problems. So what I propose is to apply some of those same insights to the domain of the international political economy to better understand how governments use treaties to deepen their economic ties to one another. The two research questions I address are, first, when do countries form preferential trade agreements? This is naturally a network question, since the choice to form a tie clearly depends on other nodes' actions. The literature on trade cooperation lends insight. And importantly, there are a number of different explanations which I test, but I want to just highlight a couple for you. As illustrated by the demise of the Trans-Pacific Partnership, domestic politics within countries clearly matters. Governments that face many constraints, as the Obama administration did when trying to float the TPP through a Republican Congress, had difficulty ratifying new treaties. So we'd want to think of the characteristics of the countries in determining the network ties. In addition, when countries form preferential trade agreements, there's a stronger incentive for countries to band together to gain economic leverage. So in this literature, Manger et al. Have identified closure effects. In other words, governments have a higher propensity of signing PTAs with others to whom they are indirectly tied. The second question is tightly linked to the first. What is the impact of the PTA network on trade flows? The political economy literature establishes that preferential trade agreements lead to an uptick in trade between members in the subsequent 5 to 10 years. The different timing of the impact has been identified when one disaggregates between intensive versus extensive margins. So how much of this effect comes from increased trade dependence? How much comes from the negative externalities of PTAs? In other words, trade diversion away from non-members. I'll speak a little bit more about the conflict with the multilateral trade regime if people are interested in that substantively. But to just give you a hypothetical cartoon of what I'm modeling, It highlights why traditional regression analysis would be unsuitable. By assuming away the effect of one node's status on another, as is required with basic regression model assumptions, we could end up with biased estimates. So you can think of, say, 4 countries which are all trading with each other. We're not going to worry about the direction, a directed network, but rather undirected bilateral trade. And we can imagine that there's 3 of these countries form a preferential trade agreement. If indeed that intensifies trade within that community, it might detract from trade outside the community, right? And so this is one hypothetical outcome, and that would incentivize a country outside the community to try to join. So this is the type of dynamic that we're interested in. Okay, so thus far I've discussed the substantive puzzle and the inferential challenges. Now I want to explain the statistical models that allow me to account for these indirect effects. For inferential network analysis, I rely on exponential random graph models. The basic version uses characteristics of each node's countries and their relationship to predict observed network of ties, PTAs. And there's variations on this ergom framework, which I'd be happy to discuss. There are a number of alternative network models which have their own strengths and weaknesses, and in a recent comparison of different network modeling alternatives, the ergom model which I choose seems to best suit the substantive puzzle. So how does this work? What is a exponential random graph model? Considers a network conditional on a series of predictor terms. These predictors, network statistics, represent configurations of ties. For example, triangles of 3 nodes with a common attribute that are hypothesized to occur more often than expected by chance. These terms, along with their coefficients, define the probability of each edge and the probability of the entire network. A trivial example is the homogeneous Bernoulli model. The configuration is an edge, the predictor is the total number of other edges, and the network may be viewed as a collection of independent and identically distributed Bernoulli random variables, like this on and off switch between pairs of nodes. Building on this baseline model, one can also account for more sophisticated networks. So suppose we want to model an empirical case where not all nodes are equally likely. This can be modeled with ergoms that obtain maximum likelihood estimates that describe the impact of local selection forces, including node and edge attributes, on the structure of a network. For example, if 2 nodes, 2 countries sharing a common attribute, for example, both low-income countries, may be more likely to form an edge, a preferential trade agreement with one another, and edges with certain attributes may be more likely to form. For example, if there's more bilateral trade shared between those countries. So this N of X term defines the support of all obtainable networks that, as a function of the nodal characteristics. If you had just one simple network statistic, like an edge count, that would enter into the vector parameters y here. If you had covariates of interest that, like whether 2 countries share a contiguous geographic border, that would kind of enter into this X term. We can talk more about the mechanics of it if that's of interest to people. The normalizing factor, this C normalizing factor, captures the summation over the sample space. And so estimating part of this is a computational challenge for the ergom models. And so to estimate these models, I rely on an R package by Hunter et al. That's available open source, so it's easy to get access to. So what do I find from my first analysis? Here, I modeled the predictors of the preferential trade agreement network at various slices of time. Bilateral trade between pairs of countries is indeed a strong predictor that they will form new PTAs with one another, even accounting for trade with other countries. Importantly, there is a strong transitivity effect. So this last term, which stands for geometric weighted edgewise shared partners, it's a whole long thing. Basically, it gives you a sense of the number of pairs of nodes that are connected by both direct edge and by two paths through another node. And this positive significant coefficient points to transitivity in the network. That's beyond what may be explained solely by nodal characteristics. This tends to suggest that countries prefer to form trade agreements with other connected countries. These plots show estimates over time. And what I just want to highlight for you here is that consistently over time, smaller economies have been more prone to form these connections. Bilateral trade is a strong predictor. And over here, in more recent years, governments that have a lot of these internal checks and balances through a different party held by, say, the legislature and the executive in the US case are less prone to form these trade agreements, which is exactly what we saw when the US failed to ratify the TPP. So it may be part of a broader trend. It's informative to compare these estimates to standard logit model results. In other words, without accounting for network effects. The table shows the two analyses with the exact same specification on the same data, save the network statistics. And trade intensity is an even stronger predictor in the network setting, suggesting that concerns about competition or trade diversion may be a little exaggerated. Okay, so an important extension to the ERG model, it takes values and the ties. And this allows one to model the strength of the ties between nodes. It introduces a non-binary reference distribution to allow for count or continuous data. So these models have some problems with degeneracy. If, for instance, if you had a very sparse or a very complete network, it would be more computationally challenging and less reliable estimates. I applied the valued ERG models to examine two additional questions. First, as I noted, trade agreements vary in their design, with some imposing more stringent obligations on their members than others. One might expect that governments that initially trade with one another choose these deeper, more stringent legal mechanisms. For example, the European Union has extremely stringent requirements over trade, whereas there are more shallow trade agreements, such as between the US and Morocco, which have very minimal requirements. So the intensity of trade predicts slightly higher prevalence of these deep, stringent trade agreements, but the differences are actually quite small. Second, and I think more interestingly, I aim to model the subsequent trade flows as a function of previous preferential trade agreements. So here the question is, does trade between member states expand in the years following the implementation of a new trade agreement? If so, is this driven by trade diversion or market growth? So this table shows the year-over-year percentage change in bilateral trade as a function of the formation of new preferential trade agreements. These ones look at the ones implemented in the preceding 5 years, although I tried all sorts of different time lags and seem to find pretty consistent results. So what this shows is reliably new preferential trade agreements lead to an expansion in trade between those countries, even accounting for other preferential trade agreements in the network. I did a number of other analyses, including focusing on the temporal aspects. Another variation of these ERG models looks at the network evolution over time. So one can model two separate processes, the formation of new ties and the dissolution of existing ties. This kind of extension, however, is substantively pretty tricky in this particular application. In the international politics literature, some scholars have highlighted the existence of so-called zombie institutions. So what this means is that countries tend to establish international agreements which eventually become obsolete, but they don't bother to disband them. And so these institutions continue to persist on paper, yet maybe have no effect on the economic relations between the governments. And with little bearing in practice. And so sometimes this happens if, sometimes they may be superseded by new international agreements. Nevertheless, the risk of this is that the dissolution of ties is not easily measurable. in a sort of substantive sense. So I did look at some of the factors that predict how durable a preferential trade agreement is, allowing for the fact that at least some of these ties will be meaningless ones. So let me just kind of wrap up some of the findings that I've shown to you today and some of the extensions that I've explored. First and most reliably, preferential trade agreement networks reflect established trade relations between countries. Once we account for the indirect effect, it's clear that countries form PTAs when they trade more together. There are clear community effects. However, there's less support for a balancing effect, in which countries form preferential trade agreements to improve bargaining leverage over others. Second, preferential trade agreements reliably promote an increase in trade, and this has been a point of contention in the literature. If I measure it as a percentage change over previous levels, I do see an uptick in trade in the subsequent 5 to 10 years. The benefits for members of PTAs appear to outweigh losses for non-members. And the ERC models do not, unfortunately, allow me to pin down whether I can attribute the causal mechanism to the trade agreement itself. Does that have any independent causal effect, or is it merely serving as a marker for future expansion in trade? In other words, we can think of it as not necessarily the case that preferential trade agreements actually prompt more trade. Rather, it's possible that these PTAs are signed when countries anticipate deepening economic relations as a way to kind of pave the way for more cooperative future interactions. So of course, given observational data, it's hard to pin down causal effects. However, third, in an analysis of these temporal models, I did find that preferential trade agreements with these legalized means for dispute resolution tend to last longer. So you can think of NAFTA as a prime example. When there's a disagreement over trade barriers that arises between, say, the US and Canada, as has been the case in many instances, those countries can engage in a quasi-judicial process to reach settlement rather than resort to trade wars and dissolve their preferential trade agreement. This tendency echoes a broader finding in the literature on international cooperation, that dispute settlement mechanisms can stabilize an international regime, making it more durable over time. And finally, there are only slight differences between different types of preferential trade agreements. Another point of interest in the literature has been whether these trade agreement networks conflict with the World Trade Organization. And here I don't find very much evidence in this respect. In effect, do countries that are dissatisfied with the multilateral trade regime as embodied by the WTO seek to secure preferential treatment outside of that umbrella? Well, in this respect, the fears might be a little exaggerated because governments that are involved in a lot of disputes within the WTO don't seem to subsequently seek more trade agreements outside of that regime. Finally, since this is an ongoing project, I want to outline for you my next steps, and hopefully that gives you some sense of where I need suggestions. So first, I'm working on rerunning the analysis, where I look instead of total trade, instead of looking at total trade, I examine the intensive and extensive margins of trade at the country level. This distinguishes between increasing volumes of trade among country pairs that already had trade of some sort. And so this allows you to get at the entry of new firms into trading relations or new product levels. And on the other hand, the initiation of trade between countries that previously had none. So there's some literature on this, and I'm kind of working through what one would expect reasonably. But one might expect that PTAs do little to open entirely new markets, but can facilitate the expansion of trade between countries whose markets are already complementary. The second point I'm working on concerns regional dynamics. As you saw, there's clear qualitative differences between regional clustering and cross-regional preferential trade agreements. And then finally, I've spent some time working on estimating the joint relation between tie selection and node variable influence in the network. Several statisticians have been working on a model that combines the ergom with random field modeling, and this is an area of active research which I've tried applying to my data. So with that said, I'd like to just wrap up, and thanks for your attention, and I look forward to your comments.
Okay, so we've got 5 minutes for discussion. Any questions? Yes?
So question, like when you test regression, so you're running binary variable, PT agreement on the binary variable real trade. Is it correct?
The trade is a continuous variable, so it's like the volume of trade.
The value, it's lagged for how many periods?
I tried between 1 and 5 years of the lag, and it's pretty consistent.
Okay. So have you tried to do like trades with bilateral trades as a percentage of GDP or something?
Yeah, so I looked at trade dependence, and then I also looked at the percentage change in trade as the outcome variable in the second portion of the analysis.
So yeah, the second question was, the second regression was not binary variable.
Correct, yeah, and the second, so the first analysis was like trade agreements as the outcome, looking at trade flows in the preceding years. The second analysis, I flip it around, clearly endogenous. However, all of these things are, so there's only so much you can do. But the outcome was a valued network, where I looked at the percentage change in trade in the years following a new preferential trade agreement.
Okay, so when you say trade, when 75, it means trade from 75 to 80?
I tried it a couple different ways, like the 1 year change and then like the levels. Yeah, and so the results I showed were like the 1 year change.
Okay.
Yeah. But, thank you.
Is it possible in your analysis to distinguish different network structures? Either you have a snake or a spider. You know, in trade literature we have this. Either you have hub and spoke relationships, or the trade is sequential.
Yes.
Data?
Yeah, so I've tried a couple different ways to like get at how much of it's like a closure where all of them are linked to each other versus like a hub and spoke kind of model. I guess I haven't found any like really striking patterns on that, but some of it's model specifications, so I gotta play around with that a little bit more. But thank you, that's good. That would be interesting. I'll push up to that point a little further.
So I'm not familiar with these models, and so I found it a little bit hard to understand what the unit of observation was, right? So like subscripts and so on would help. And one of the things I know is that if you just look at bilateral trade between countries, and then you're dealing with country pairs, there's a real serious problem with inference, right? That you have to allow for correlations across country pairs, and the models that we use do not pick up all that correlations. In fact, with my own work, I found out that you can be out by a factor of 3 or 3 to 5 on the standard errors. So I can't tell from these models, but is that an issue here? I mean, is the standard errors that you're getting, do they adequately control for interdependencies? Right? Is there?
Yeah, I mean, in theory, yes, but I don't have any like good measures to tell you how much inflation or deflation of those standard errors there is.
Well, if anything happens, it'll be inflation. The question is whether there is inflation. And then the other thing was, with these models, they're non-linear models. To what extent are the results that you give just simply statistical significance versus meaningful economic magnitudes, right? So there are a lot of stars, but were these big effects or small effects? So for example, towards the end, it said percentage changes, and then I saw numbers like 0.77, right, which to me, 0.77% is very small. Yes.
I think with the ERGM, it's a really complicated stats, but the concept is really similar to logistic regression. And the coefficients that you get with this model, you can actually get the odds ratio. And then that is a measure that a lot of people at the university level can understand better than other little steps of this.
Okay, so it'd be good to translate.
I think so, that's what I've done.
Yeah, I started down that route by doing a comparison to the standard logistic results, and so I'll push that further to get a sense of scale. Thank you.
Okay. Well, thank you again. Oh, sorry. The PDFs, it's one of these PDFs down the bottom. One's yours, one's mine. Control. If you keep going down full screen mode.
Alright, well, my name is Tyler Scott. I'm actually brand new here to campus over in Wixon Hall in Environmental Science and Policy, and so I'm pretty proud of myself for actually finding my way to this building today. So, off to a good start. This sort of encapsulates my research topic, but essentially the talk I'm giving today is really network analysis in a messy world. So you might not care about forests and fish and water and environmental governance, but many of you probably do have network type applications and likely some messy data. So hopefully this can speak to that. There's a lot to digest in computational social science, and so one of the themes today of what I'm going to present is that even if you don't know how to do all of it, and you're not the best at all of it, there's some really simple tools and strategies that you can use in your particular messy applications. So for me, what that looks like is I study coordination and institutional complexity, and I'll show an example of that in environmental governance. And so this is my story about how I combine text mining and graph models, ergo models, as Lauren already presented, to get at these questions that I'm most interested in. So here's my first example. You've probably seen a lot in the news recently about the city of Houston. It's a great example about institutional complexity in environmental governance. There are more than 1,400 different independently regulated water providers just in the Houston metropolitan area, which is just a ridiculous number of independent utilities, right? And they, because of that, they face significant coordination problems. So they're all fighting for the same supply resources. They all have straws in the same groundwater aquifers. They're fighting for infrastructure and finance, the ability to sort of tax and spend. And then they have to coordinate on all sorts of service delivery challenges as well, because obviously not all 1,400 of these systems have the capacity to sort of go it on their own. And particularly, a lot of these are essentially like you and your neighbors in your cul-de-sac decided we're going to form our own water utility. So lots of interesting coordination problems when you have like these local neighborhoods who are also sort of operating almost as their own city. And it's obviously been in the news recently since Hurricane Harvey. You've probably, if you read a lot of these articles, it'll often mention a lot of these small utilities. These are the ones that are having trouble getting back on track. They're not sure what the quality of their water is. It's not the city of Houston in the center here. It's all of these tiny thousands of districts out in the outskirts. So if I'm interested in how they coordinate and how they share information, how they provide clean water, the classic way we've done that in social science when we're studying environmental governance is with surveys. And they pose issues that many of you are all familiar with. So the first one is recall. It's one thing to ask students in a high school classroom, who are your friends in class? There's only 30 people, they can sort of think through all of that and name their friends. It's another to ask people in that type of complex institutional environment, who are all the people you coordinate with? Second, even if they did answer that, even if you had all the time and money in the world to keep rolling out your own surveys, these folks are busy. And they don't have time, they don't really want to answer your surveys. And so even if they do have perfect recall and you have all the monies, you're still not going to be able to get good results going forward because ultimately we care about how this changes over time. And so we have significant problems with repeating our surveys as well. And this is sort of an idiosyncratic feature, but it also sort of shows up, I think, in Lauren's data as well. We get this sort of like person-organization fuzziness, or in her case it might be company-country fuzziness, where we're sort of, it's like I send a survey to these water providers, and one person gets it and they fill out, who are my coordination partners? But if you think about like the city of Houston, they have hundreds of employees, and so if you get that goes to someone else, maybe they talk with a completely different subset of organizations. Whereas if it goes to a small organization, that one person might be able to speak authoritatively to all of their network connections. And so really in practice what this means is your discussion section gets longer, as you sort of justify to reviewers why you think it's okay to sort of aggregate to organizations. But it's nonetheless sort of an ongoing latent problem that's sort of always bubbling in the undercurrent, is what are these nodes actually representing? And surveys also, particularly when we zoom down to sort of local and low-level governance, they miss key things. So one issue here is these types of small operators, they're not necessarily showing up in large-scale regional planning meetings, right? So we have sort of this high-level, like big agencies, big municipalities doing things like regional coordination bodies, and then we have these small folks who are just trying to keep the water going. And so they're not going to show up if you survey like regional coordination bodies. And they also likely, if you ask, well, who are your collaborators, they're not going to list their actual collaborators. They're not going to list the people you care about, like the person they pay to do their taxes, and the person they pay to keep the water going, and their finance expert, and things like that. So one thing that my co-authors and I are always trying to think through is how can we better measure coordination in these types of networks without having to resort to survey data? And so one thing we've hit upon is personnel records as an alternative network measure. So when there's lots of evidence that shows that expertise, skilled labor, is a key driver of environmental outcomes in service delivery. So you have to have access to people who know how to treat water, who know how to operate a debt financing scheme, things like that. And so it's a key driver of outcomes they all have to rely on. And the cool part about studying these types of administrative processes is they also all have to file lots of administrative records. So like you can go to the state of Texas's government website, and there's a page for every single water provider, and it lists all their contacts, all the licensed technicians they employ, all of their other experts that are on their payroll. And so what we argue is that personnel who work for multiple providers are a conduit for information sharing and connectivity, just like social relationships might be. And so instead of a social relation connecting two nodes, we're actually going to use people as a connection. So when you think about that, one question isn't necessarily interesting at all, right? Because small providers are inherently going to share due to sort of the transaction cost economic logic, right? They don't need a full-time employee, so they pay someone part-time. So we're not interested in predicting contracting because that's already sort of well settled. What we're interested in is asking this question of, if I'm going to share, who do I share with? Do I share with people I'm competing with? Do I share with large organizations, small organizations, those types of questions? So here's a little bit about what this network looks like. So we're going to use a bipartite network graph, and that's essentially just a two-level network. So on one level, we have people, and on one level, we have organizations. And thankfully, Lauren's already done a lot of the heavy lifting in explaining how ergoms work, so I don't have to get into that too much. Essentially, as someone in the back mentioned, we're talking about a fancy logit. And in essence, you could use a logit model to estimate the same thing, or you could estimate your logit model in an ergom. What sets apart an ergom typically is we don't just have system attributes, like what kind of system you are and how big are you. We have these autoaggressive structural terms. And these can get complex if you sort of wade into the sociology literature for all the names they have for them. But if you're familiar with like a spatial modeling application, it's a similar type thing. We're simply regressing, we're simply controlling for surrounding ties on a given tie that we're trying to predict. We're saying that your neighbors matter. So if I run a water utility and you run a water utility and we already share one person, and you might be more likely to share another as well, that type of thing. The other interesting thing is sort of a messy network problem. It's very common when you start out with a two-mode network to actually collapse the matrix, take the cross products, so you get a one-mode network. But that would be sort of weird in this case, because you'd start with this person who works for three systems and you'd collapse it, and then what you'd be modeling is a full set of ties between all of these nodes. So an example would be the graph that Lauren showed again, where you saw that in some of these bilateral trade agreements, because everyone's part of the agreement, everyone has a tie with everyone else. And that can pose some serious modeling challenges when you have one contractor who works for 10 different systems, and then you tell the model, all 10 of these organizations have a tie to each other. It's also, I guess I should say, I think it's also sort of more conceptually appropriate in this case, because this really is what our network looks like, and so otherwise you'd be sort of obfuscating that. So a couple quick hitting results. So as sort of a proof of concept, size behaves as it should, right? We simply see more employees, and because you have more employees, you're on the margin more likely to at least share someone if you're a large provider. Questions more interested in, there's lots of small providers who are drawing upon the same groundwater aquifer, and the way Texas works is if you have a straw in that drink, you can pull out as much as you want. And they have lots of carrots trying to get people to stop, but it's a massive collective action problem. And so one thing that's actually interesting about this is we wouldn't expect that these providers competing for the same resource share personnel, because that information about what they're doing gets back and forth. But if we're sort of looking at it from another direction, this might be a way to help all of them actually work together towards the collective solution that these regional groundwater authorities are hoping they work towards. Another example, and the standard errors are somewhat large on this, but again, we're really just interested at this point as a proof of concept in which direction these effects are moving. We see that districts that buy and sell from one another are also likely to share personnel. So plans for building on this, because I think as a first step, it's even important just to demonstrate that these types of network ties follow sort of basic intuition. We intend to connect personnel sharing to performance outcomes, particularly things pre and post Hurricane Harvey, looking at who you employ and what employees you share, how that affects how quickly you were able to get back online, and then maybe inverting that and looking at turnover and asking if you had sort of a severe event when the hurricane hit, did you end up sort of switching and going with some other personnel? Data collection is ongoing for this, and what that essentially looks like is every month my Google Calendar sends me a ping and I fire up the web scraper again and I go to all the different district websites and scrape everything. So hopefully in a couple of years we'll have something pretty cool. Because that's ongoing, I'm going to pivot quickly to another example to show how we take these types of data and try and extend them over time. So the second example is hydropower facility relicensing that's run by the Federal Energy Regulatory Commission. And it's a really cool example of environmental collaboration because FERC actually says you all have to collaborate. So this isn't a case where everyone says, hey, let's work together, this will be great. This is a case where a federal agency says you all need to get your act together and work this out, or else this is just going to go to court forever, and no one really wants that. So what we see in these cases, it might be one small dam way up in the mountains somewhere. So like the case we analyze is way up in the North Cascades National Park. And we still have tons of different stakeholder groups, so private firms, resource agencies, local citizens, local towns. And the challenge they have to come together on is to develop a 30 to 50-year operating plan to specify all the contingencies about how they're going to operate this dam to provide energy and protect fish and do all sorts of other things for the next 30 to 50 years. So the types of questions that I'm interested in looking at these sorts of processes, a mandated instance of collaboration is, well, who actually shows up when FERC says you all have to do this? Who becomes a leader in the process, or who sort of maintains leadership throughout the time? Or who leaves, right? One thing we might be concerned about is a collaborative institution becomes a coalition over time as sort of peripheral people drop out, and it's sort of collaborative in name only at that point. So the challenge of this type of process is it's way too big to hand code, and it's way too long to survey. So we're looking at, again, one relatively small dam way up in the mountains in the state of Washington, and this takes 16 years. And they held more than 600 meetings. We're able to find meeting summaries for 591 of them. And no one wants to read through all those. And we also can't really follow up with a survey and ask people, like, what was your participation like? Because they just can't give us good responses over what they did for the past 16 years. Thankfully, as I said, someone does take notes. And so that's sort of our point of entry into analyzing this type of thing. So the first thing we're interested in is who shows up. And so we're going to perform a text mining, we're going to use a text mining tool called entity extraction. And essentially how it works is it takes these meeting summaries and it tokenizes them into phrases. And I say phrases, not words, because some phrases like fast food are actually one word, right? And so it uses a machine learning classification tool to say, like, this is a word, but this compound word is a word as well. And then we're going to, again, use a different machine learning technique. It's a pre-trained classifier that then looks at these parts, these words or phrases, and says, this is a person, this is a location, this is a date, this is a number. So pretty basic. Ultimately, it's statistics on the back end, right? Because these machine learning algorithms have been pre-trained on, thousands of books, and they use that pre-training, that data set to then say, looking at this new sentence I've never seen before, I think that is also a person's name. And so but once we get this extracted set of people who show up in these meetings, we supplement it with hand-holding. So a few examples of what that looks like, because real people had to write these meeting notes, there's misspellings. So we use fuzzy regular expression matching to pick up where, like, David has the I and the V reversed, things like that. Another example would be, if you've ever heard of a Dolly Varden, it's actually a kind of trout. But IBM's sort of baseline classifier doesn't know that that's not a person, that's a fish. And so that would be something going forward as we build our own customized model, we'll pick that up. But for now, we filter that out on the back end. So we don't just want to know who shows up, we also want to know what they're doing when they arrive. And so the second text mining tool we're going to use is part of speech tagging. So this time, we're going to take these texts and we're going to break them up into sentences rather than phrases. And then we're going to feed it back into a machine learning classifier, and it's going to spit us back out a probabilistic model that says this is the object of the sentence, this is the subject of the sentence, and this is the verb. And here we're particularly interested in subject and verb. So the person who's doing something and what they're doing. So a quick snapshot of how we're doing when we actually try and run these things. We hand-coded 50 different meetings. And so on the top you can see how we perform with respect to attendance. The machine has false positives, but it doesn't have false negatives because it's not going to generate a name out of thin air. So it's only going to find cases where someone wasn't actually in the meeting, but their name came up. So it might be a reference to President Obama, or it might be someone saying, let's invite so-and-so next time. And so that's why the hand coding tends to track below machine coding, is because some of those names weren't actually present. When we look at the part of speech tagging, we're a little more all over the board. We hit and miss, high or sometimes high, mainly low. This is a noisy thing even for human coders. It was actually sort of vexing when we sat down to code 50 meeting minutes, how much ambiguity there was even for us in saying who did what, and dealing with things like generic nouns that referred to multiple sets of people. And so I think this is sort of an ongoing thing to be explored. And then the final step, and we use this very simply right now, but we take the verbs that come out the back end and we feed them into the VerbNet lexicon dictionary. Linguists are all about verbs, and they have great classifiers that will tell you way more than you want to know about what this verb is and what it means. Right now we use it to filter out past tense and future tense verbs. So we don't want to know what someone did in the last meeting. We don't want to know what they're going to do next time. We want to know what happened in each particular meeting. One other thing that you likely find if you applied this is the way that people write up these types of documents is very different than how we formally classify language. And so Watson's program thinks there's a lot of physical activity going on at these meetings, because every time someone gives a presentation, the person who's taking the notes says, so-and-so walked us through the new report. Right? And so it says, wow, these people are walking around, there's lots of activity, and there's sort of a weird, that's why we use this for filtering right now and not for a lot of analysis, because we need to spend a lot more time with these verb types. So again, thankfully Lauren did all the heavy lifting. Essentially here, we're going to use a temporal ergon model. And we're going to use Philip Liefeld's Betergum package. It's not quite as complex as it sounds. It's essentially a bootstrap version of the type of temporal ergon that Lauren is using. The big advantage here is it has a major speed bump. So it uses a pseudo-likelihood estimator and then bootstraps that so the standard errors are not biased downwards. And the upshot, and I know it sounds silly to say a large network when I have like 770 people, right? That's small data. But for ergon models, that can be a big deal. Right? So when you have upwards of 500 nodes and you're fitting an MCMC-driven ergon model, if you're not careful, that can be weeks, right? Or you might never even get a fit. And so the ability to get something that gives you results in a minute is a big plus. And so that's sort of the exciting takeaway about Betergum versus a lot of the other ergon modeling tools that are out there. And essentially, we're just modeling this network change over time across these meetings. So a quick snapshot of the types of things we learned from this. We find that the people who started out as leaders, they're leaders the whole time. So people don't sort of rise up somewhere in the 16-year process and take charge. If you're in charge at the start, you're going to dominate the conversation at the end. We find that anyone who FERC said, this person has a key sign-off role, they tend to dominate the conversation as well. If you've been sort of empowered with a little bit of veto power, you're going to talk more, you're going to present more, you're going to dominate the process. The interesting thing is after the license is approved, it enters this 5-year implementation phase, and there's no more mandate to collaborate. And so what we see after this phase, when we interact the stability of individual interactions with this phase, is that the stability drops, right? And so we see less regular interactions, we see people who sort of show up in one meeting and they don't show up again for a year. So it appears that that mandate from FERC does sort of provide some key support that keeps people coming and keeps them participating, which matters because meetings suck, right? And it takes time to drive there, and you have better things to do. And so anything you can do to sort of support people continuing in this type of collaborative process can be valuable. So wrapping up, for a lot of network research, actually running the model, it's like 10% of the work, right? getting a network that you can model is you know, the real hurdle. And if you can pull it off, right, graph models are useful even if you do not have something that's sort of a standard network. Right? So a lot of times we think that it has to be sort of a truly social network, but really what we use graph models for is when we think there's some sort of structural interdependence, when we think that the neighboring ties matter. So whatever your nodes and edges are, if you think there's some sort of interdependence that you can't capture simply by sort of applying like fixed effects or random effects for particular actors, you might need to explore an ergom type approach. And then finally, if I can do this, any of you can, right? This is not high-level text mining, for instance. Someone like Dan is so far beyond in terms of what he's actually doing when he's processing language. We're doing fairly simple things like spitting out people and spitting out the actions they take, but we can learn a lot from that. So I'm excited about sort of applying these types of simple tools to important real-world problems. So with that, thank you, and I look forward to your feedback.
Questions? Okay, so I'll ask some questions.
Sure.
So we see a lot of stuff about network and these graphical models, and it's a very active area at the moment. Is there a good reference?
Yes. My favorite is the Lusher et al. Book, which I think one of your advisors is also an author on, right? Mark Hancock?
Yeah.
So that's my favorite textbook.
Yeah.
But a lot of it lives online, right? So the StatNet webpage housed at the University of Washington has a ton of resources. They have a super active user group. So I think the first thing I'd go to is statnet.org.
Well, yeah, but the thing is that, you know, a lot of us are actually fairly knowledgeable on statistical methods in general. And
Well, so
and my view is if it's a question of finding the reference. Right? I can wade through a lot of papers, but presumably there's one or two papers out there that, for instance, would explain when we say bootstrap, you need to bootstrap over something that's independent, right? You can easily do an incorrect bootstrap. So I'd be interested to know, for example, how does, you know, what's the resampling scheme that's being used?
Yeah, so the way that one works is it's Skylar Kramer and Bruce Desmarais. And what they do is it only works for temporal network models because they actually resample those network periods, right? So they'll pull a set randomly and they'll run the model on those and then they'll do it again. And so they have a 2012 paper, and I forget where it's published, but it essentially shows that when they apply that method with the pseudo-likelihood estimator for a temporal ergom, they do generate unbiased standard errors. But so I think the high-hanging fruit out there is still figuring out how we can do a similar thing for a non-temporal network model.
Okay, any other questions? Okay, well, thank you again. So let me start. We read all this stuff about machine learning, deep learning, this, that, and the other. I mean, the previous paper in particular showed a lot of the tools out there that are being used, and I know really nothing about this, but I just want to know things, right? So I committed rather foolishly to teaching a PhD course where I spent 6 weeks on machine learning to force myself to learn basically what it is, and spend a lot of time on it and so on. I figure I can explain it in 30 minutes, so we'll see how that goes. Okay, so this is the key, this slide, right? The goal with the machine learning is prediction, right? That's the goal, which is often different from a lot of what we want to do, which is to get a beta hack, right? Which has some physical interpretation. And in pure machine learning, there's no structural model. There's no knowledge that, you know, there's a gravity model of trade, and the trade flows between countries will depend on, you know, the size of the countries, the distance from the countries, and so on. It's just thrown in this data, and then there's some algorithm, and given that algorithm, it spits out an answer, right? So there's no kind of structural model, no model behind, in the purest form of machine learning. That's why it's called machine learning, right? but it's an algorithm, right? And it's using existing data, okay? These train the machine to come up with a prediction model, and then this model is then used to apply it to a different set of data to make some predictions, right? What we would call that is out-of-sample forecasting, right? That's what it is, okay? And then you've got to be concerned about overfitting the existing data, right? So, if you like, there's some true expected model of y conditional on x. That's what we want to fit, but what it's aiming for is the y hats that we observe, right? So if there's an outlier, it's going to be chasing to get that outlier and explain that outlier. Well, when you apply it to a different data set, the outliers are somewhere else, right? It's just not going to do as well. So there are methods to guard against overfitting. And this is really something that we just don't do very much of, right? If an adjusted R-squared is some attempt, but really I'd say this is perhaps the biggest difference between machine learning and what we do, right? I think there's a lot more concern about overfitting, right? There are lots of different algorithms, right? They go by names like deep nets, lasso, and so on, right? They're just, and it's rather like, there's a logit model, there's a Poisson model, there's a whatever, right? But there's so many of them. And this is the hard thing, the different algorithms work better on different types of data, right? So a regression tree might be fantastic for one type of problem, but hopeless on some other problem. For some other problem you want, I don't know, what a neural net or lasso. Okay? And then, as we saw from the previous talk, forming the data to input can be an art in itself. Right? There's a term for this is data carpentry. So, generally in the problems certainly that I work and I see people working on, usually they've got a good idea about what y is and what the x's would be. Right? But don't ask me how you get data out of a photo of a face and then do facial recognition, right? How do you get Y's and X's out of that? I have no idea, right? But the thing is, that's a problem that a lot of people are dealing in. So people who deal in that problem have got off-the-shelf algorithm methods to capture the features, right? It'll be distance between the eyes, it'll be, etc. And what could go wrong? How could we, well, we always say correlation does not imply causation, right? This is where, in any field, your knowledge, your base knowledge, the starting point is that, trade will depend on these distances and so on. And then, as we said in the first talk, the trade partnerships, will matter, right? And the challenge here is you bring in the models, you bring in some structure, but also we know that getting causal inference can be difficult. And what people are doing is, if you have some causal approach that along the way requires that some part of it be flexibly modeled, then maybe we use the machine learner to get that flexible modeling part and put it back in with the rest of our methods. But then we have to make sure our inference guards against the fact that we could be back in an overfitting situation when we use the machine learning. Okay? So this is the bottom line, right? This is what's going on. And then a lot of my talk is just now, I think, mentioning buzzwords. I'll be good. It's behind.
I stole it.
Let's get to that. Okay, so the topic is called machine learning, but other names are statistical learning, data analytics. And the big thing is the term big data is used, but it doesn't have to be big data. And then the literature distinguishes between supervised learning, where there is a y and an x, and we call that regression. And then there's regression where our outcome, well, is continuous, but it could also be, say, a count or whatever, but it's one that we have some, I guess, cardinal measure, right? 6 is 2 times 3, right? The alternative is classification, right? Which, you know, is well, where we would use a logit model or a multinomial model, okay? And then unsupervised learning, there's no y, right? Unsupervised learning, we're just trying to get x's and see some pattern in them. And a big one would be in psychometrics, where we've got all these attributes on people, we put them together, and we see, oh, there's this cluster of people that have these common attributes, and then we look at them and we say, oh, yeah, it looks like that person's an aggressive person, we'll say that's a type A individual. So, what I'm going to focus on is just the first one, regression. Okay. So a little bit about classification and really almost nothing about cluster analysis. Okay, so a big thing is this not overfitting. So the term is, you know, a training data set or an estimation sample, and then a test data set or a holdout sample or a validation set. Okay, and then kind of the fitting of the model is here, and then deciding whether it's good or not, you know, having a race between different models would be using, so in a way we might get the beta hats from here and then use it in predicting here, and then see which model was getting beta hats that did a better job of predicting here. So I've got an OLS example, and the big thing is mean squared error. With a machine learner, you're going to have a loss function, right? And the loss function that's used for continuous data is mean squared error. And think of this as, say, we had multiple observations when x was 1. So this might even be quite precisely estimated. This is the average of them. And then with lots when it was 2, and so on. Okay. So, you know, which should I go for? Should I go for the line that connects the dots, or should I do some sort of smoothing, right? And what mean squared error is doing is it's balancing the two, right? So, you know, this prediction here could be biased, right? The truth is somewhat higher, but I've got a smoother fit. And mean squared error is the sum of bias squared plus variance. But a lot of the machine learners use biased estimators, right? And even, you know, asymptotically because of this smoothness property. Right? And one place where, if you're familiar with non-parametric regression, right? Non-parametric regression, if you use cross-validation, that's essentially using this mean squared error trade-off. Okay, so I create an example where the data is quadratic, the data generating process, believe it or not, but when I run the regression, I do a quartic and it's having a hard time deciding whether it's x cubed or x4 or x squared is most important. But here, I set it up so that I had 20 observations here and 20 here, and I had set it up so that the x's were the same, right, in my estimation sample and my validation sample. But on using these data, the quartic I fit is this. So now I've got the same x's over here, so it's going to be the same predictions. But I'm comparing to actual data, and you can see that I'm just getting more outliers here, right? It's just not predicting as well out of sample. Okay? So when I do things in sample with the linear model, quadratic, cubic, quartic, it's getting better and better and better. But when I go out of sample, right, the lowest is actually the quadratic, which was the data generating process I used here. Right? Now, it didn't necessarily have to be this way, but in most simulations it's going to turn out that we, because there is randomness here. So I just have this here to try and show that it's very easy to go wrong, and particularly to overfit. Right, this is saying that a quartic is best when my data generating process was a quadratic. Okay, so what can we do? Well, what I've done here is basic validation, but I've lost precision. Right? To do this, I had to say I've got 40 observations, I'll only use 20 in estimation. So I can have this other 20 outside for my validation. And then furthermore, the results will depend, where do I do the split? Right? There's many 50-50 splits I can do with the data. Okay? So what k-fold cross-validation does, here I've got, say, 5 splits. We randomly split the data into fifths. We estimate on 4/5 of the data and predict on the other 1/5. And we can do that 5 times, right? So first, I hold out the first fold, estimate on the others. Then I'll predict on I'll then use those estimates on the other folds for the first fold. Now, I'll hold out the second fold. So I'll estimate on the first, third, fourth, fifth, get beta hats there, and then predict on the second fold. So this is doing this is where I left the first fold out, what the root mean squared error I got was, when I left the second fold out, third, fourth, fifth. And this was for one particular model for the quadratic. Okay? And then the average is 12.3935. Okay, so I've 5 times estimated models on 4/5 of the data and predicted on the 5th, and I've got the average mean squared error across those 5. So now I'm going to do the same thing, not just for the quadratic, but for the linear model, the quadratic, cubic, and quartic. And we'll see which gives the best result. And then I don't know why this is actually, when I look at it, why the linear came up with the same as the quadratic. But it is showing the quadratic has the lowest mean squared error. Okay? And again, because of randomness and only 20 observations and 40 observations, didn't necessarily have to turn out that way. But with high probability, it would turn out on any realization of a random sample. Okay. So I spent a lot of time on that because I really think that forces us to think a little bit about what we're doing in our own work, right? Whether we run the risk of overfitting. Okay, when you put structure on the model, so for example, it's a linear regression with, well, for example, if I have a log likelihood function, right? So that's a quite structural model. In that case, there is theory out there on information criteria which give a penalty for model size. Okay, so the bigger the model, right, we maximize the likelihood as we have more complex models, better fit, the log likelihood goes up, minus the log likelihood goes down. We want this to be small, but then there's a penalty. Right? AIC actually is a pretty weak penalty. This is a bigger penalty, Bayesian information criteria. Okay, and there are other ones, Mallows, CP, one we've just seen is adjusted R squared. They're much more model specific, and in some circumstances, you can show that cross-validation is doing the same thing. Cross-validation is just a universal thing, but it's computationally more expensive. And maybe you can do this. For some problems this may be good, and maybe for some initial analysis speed things up, and then later on do a proper cross-validation, or proper, even cross-validation. I mean, it's pretty arbitrary. Why is it that we're using bias squared plus variance? Why not 2 times bias squared plus variance? Okay, as our loss function, but we use bias squared plus variance. Right, which underlying it has a squared error. Why use a squared loss? Why not use an absolute loss? So I mean, there is arbitrariness. Okay, so when we use AIC and BIC in this example, they both come up with the quadratic again being best. Because the AIC didn't have such a big penalty, there wasn't so much difference between the quadratic and the quartic, whereas there was a bigger difference with the BIC. Okay. All right, so now we're getting into regression. And the first thing is that generally you think, linear regression, pretty restrictive, right? But if you had a ton of data and you could put in all sorts of interactions and quadratics and so on, right? A linear regression might actually do a very good job of predicting. Right? And it's easy to work with. When we say linear regression, with all those interactions and so on, it is non-linear in the explanatory variables, but it's linear in parameters, right? And that makes it very quick and fast to estimate. Okay. So, and then the other reason for going with linear regression is, that's the basis of more complex models. Okay, so methods to reduce model complexity. Don't go too overboard. Choose a subset of regressors. Shrink regression coefficients towards 0. Reduce the dimension of regressors. So, say we've got 100 regressors, I'll just go with the best 10 linear combinations of those regressors in terms of fit. So I'll go through these, and this one right here, may predict well, conclude interactions and powers. Okay, so this would be easiest if you had something like just on regressing, well, this assumes we've decided these are the 133 regressors I'm going to go with, right? And I bring in my interactions and so on. And then we want to choose which are the best 133. Okay? And there are these methods to say, okay, let's first of all have a rule for deciding if we only put one regressor in, what would be the best regressor? 2, what would be the best? 3. So then you come up with the best model for 1, 2, 3, up to 133. And then you go and do the cross-validation and say which of those is best predicting out of sample. And our cross-validation, or we could use AIC, right? Something that penalizes the model size. In R, it's all automated, right? It'll just give once it's set up, it will be a one-line command that will, spit out what the best. It's this model with 37 regressors and these 37 regressors. Okay, and then not only that, but this is a standard problem, so the algorithm methods that are used will be about 100,000 times faster than if you tried to code it up yourself. There's a thing called a leaps and bounds procedure that makes this pretty quick. Variance bias trade-off. Okay, so I kind of explained that already. Shrinkage methods. Okay, so what shrinkage methods do is our loss function is the sum of squared residuals, and to avoid overfitting, to reduce model complexity, they shrink towards 0. Right? And one way to shrink towards 0 is what we typically do, which is it's either in the model or it's not. Right? So we test statistical significance of regressors, and in some areas you'll exclude things that are statistically insignificant. Okay? Well, the lasso is doing that, but it's not doing that using statistical significance. Okay, and these shrinkage methods are on the parameters itself, on the betas. And the simplest ones treat each beta as having the same impact, right? And so a standard thing to do is you have to rescale the regresses and standardize them so that they each have mean 0, variance 1, right? In that case, each beta is telling me if I have a 1 standard deviation change in this x, then what is the change in y? Now it's not clear that's necessarily the best. I mean, what's the difference between a 1 standard deviation change in x versus a 1 standard deviation change in x squared? Right? Maybe I should have something cleverer than that, but this is the default. And if you wanted to standardize your data in some other way, you could always do it and put it into these methods. Okay. So the ridge penalty is a multiple of the sum of the squared coefficients, and the lasso penalty is a multiple of the absolute value. Okay, so let's first of all do ridge. So the ridge, we're going to minimize the sum of squared residuals plus the sum, this sum. So as we add more regresses, this is going to go up. That's a penalty, because we want to get this thing down. And then this lambda is a tuning parameter. This lambda is like a bandwidth when you're doing a non-parametric regression, right? And one can use cross-validation methods to choose the bandwidth parameter. Okay? Or you could use AIC, BIC. Okay? When you go through the algebra, I just put this in. The ridge estimator, it's x transpose x inverse plus lambda I inverse x transpose y. Okay? So that makes it clear we're dealing with what we would think of as a biased estimator, right? Because these squares would be this. Okay, now what the ridge does, it shrinks all coefficients towards 0. Okay, and as I've got here, algorithms is just to quickly compute many different values. And again, this is all in the lasso has an absolute loss, and this next diagram shows what's going on. So for the ridge, we've got beta 1 and beta 2. Okay, so we're minimizing sum over I, yi minus beta 1 xi minus beta 2 xi all squared. So that's going to give us, that's a quadratic. So we'll have these ellipses, and this is what OLS would have given us, right? And then, but we're restricting ourselves to beta 1 hat squared plus beta 2 hat squared being in here. So we're going to have to, to move down in this direction. As we move down in this direction, we're moving away from our minimizing the sum of squared residuals. So this is a larger sum of squared residuals, a larger squared still sum of squared residuals, a larger still, and this is the best we can do subject to the constraint. And because we've got this circle for our, where we're constraining things to be, and this is an ellipse, we're very likely to be where both beta 1 and beta 2. We're not likely to be here or here. Right. Whereas with that lasso, the lasso, it was in terms of absolute value. So this is our constraint. And now, for a variety of ellipses, we're much likely to be at a corner. And a corner means we're dropping something. And lasso, particularly, certainly in the econometric literature, has been very popular because of this dropping of lasso. So dimension reduction, like I said, it's just going from tons of x's to a smaller number of linear combinations of x's, so principal components, factor analysis. high-dimensional models. What that means is that P is large relative to N. In that case, there can be some problems that some of the methods, require that we have more observations than parameters, but there are some solutions. Nonlinear models. Okay. So polynomial regression, I've already talked about that, quadratics and so on. Step functions, regression splines, smoothing splines, V-splines, wavelets. What these methods do is kind of break it into pieces, and the simplest would be if I had a scalar x to just split it into all of the x's, split into deciles, and just fit a linear regression on the lowest 10% of the x's, and then another one on the next 10%, another one, and then make sure that those connect. Okay. Well, the big one of these is cubic splines. So it's done with a cubic regression, and you can very easily set it up. It's very simple to not only have them touch, so it's connected, but the first derivatives and the second derivatives at the point where they touch are the same. And then those methods, what they'll do is, you do worry about the tail points going out too far, so they'll linearize at the tail. Okay? And from what I can see, to me, maybe this problem is moving it to multi-dimensional, but for a one-dimensional thing, to me it just makes so much more sense than doing local polynomial regression like local linear. Right? I think a big reason for this is you can prove a lot more things. But these generally have a fixed bandwidth. This essentially is allowing things to vary. If you're working, it doesn't have to be every 10% of the data, but there where your data is narrow, right? You're still using the same number of observations as when you're in a sparse area of the x's. I'm just trying to give you an idea of just how much stuff there's out there, right? Any one thing is not going to be too hard, right? If someone can tell you, for your problem, these are the machine learning methods that are out there and so on, you're in business, right? But if you have to go out on your own, no, you want to go and talk to someone who's spent many years knowing about all these different methods and knowing which is the best. Okay. Neural networks. The neural networks, so y is predicted by x's, and what it'll say is that my prediction function will be this, and this is a linear combination of some z's, and then the z's in turn are linear combinations of things that are lower layer, and you keep going back until you get to, right, so it's a linear combination of this, and then somehow or other we're tying all these things together next level, we're getting more and more and more and more, and somehow or other this works fantastically. Okay. So they're particularly good for prediction, speech recognition, image recognition. Google Translate. Google Translate was trying to do things the way we do things. It was trying to teach what the rules of language were, right? Here's the dictionary. Here's how we do put things together in English. Here's how we put them together in French, right? And then they got this guy from Toronto to come in, and with about 10 people working with him in 3 months, he'd improved things as much as Google Translate doing things the old way, being able to improve things over the last few years, right? And so all of a sudden they threw all their resources in, and then once they've done it for, one lot of translation, they're doing several translations a week, okay? And so there's this off-the-shelf shelf software, right? So first of all, you use things to, get your image or text or whatever into some sort of data. The deep net is estimated using a thing called stochastic gradient descent. So you bring randomness into the, whatever, we use something like a Newton-Raphson algorithm. There are these programs out there, I've been to their websites and they promise you the world and it's all very easy. I haven't tested that theory out. Okay, I'm almost out of time. Regression trees. Okay, so regression trees, you simply use squared error loss. So the original one is the sum of yi minus y bar squared. Okay. Then what you do is you think of every possible way I could split up my data. And that'll give me basically, and then we'll use the means of those two splits. Right? So this is discovered that if I do this split at education less than or equal to 12 and education greater than 12, the sum of yi minus y1 bar squared over these people plus the sum over yi minus y2 bar squared of these people, it's the smallest with that split. And then we do things again and think of every split. And it turns out here the next thing to do was to split this into something, right, by male, female. Then age, then, right, and you get the tree, okay? The trouble with this regression tree is it's what's called a greedy algorithm. When it made the split here, it didn't think about the consequences further down, right? Once it splits here, it's just set forever. So more refined things, random forests and so on, what they do is they bring in randomness. So one way to do it would be to subsample your data and get trees going on these subsamples, right? And I don't have time to go through all of them, but we've got all this thing here. And then some of these methods are ways of getting a number of different predictions. Maybe, we started the tree this way, we started this way, and so on. And combining forecasts. And combining forecasts is viewed as the best thing to do usually. So there's an annual prediction competition around the world between teams of graduate students. And was it last year or the year before that the stat department here at Davis won it, the graduate students. And they were using about 4 different prediction methods. And their data was simply coding from from some internet shopping company, and all they had were these numbers and letters. And there wasn't even anything saying the first 3 digits mean something, one variable, and the next 6 or something. It was just complete, and they had, somehow or other they used these machine learners and so on to get some good predictions. Classification. So now we've got categories and there's no natural ordering. So there, the simplest thing would be a logit model. And then a lot of people use linear and quadratic discriminant analysis that support vector classifiers and support vector machines generalizations. Oh, I'm way over. Okay, challenging. Unsupervised learning, challenging. Causal inference. So basically the idea with the causal inference is if you're familiar with selection on observables, right? So if I could just get the right controls in there, then, and I'm only interested in one other variable, then I could believe my results, okay? So what we want is to have get really good controls. Well, if you could use a machine learner to get those controls, the machine learner is going to do a better job of prediction. It's going to, and then your controls will be controlling for more, and then you might feel better about assuming that anything that hasn't been explained is not going to be correlated with the variable of interest. So that's one example. And I've got this here. So just to finish off, okay. If you go to my website, I've got you have to go down a little bit, but I've got this thing here, machine learning, and I've got like 120 slides here, and discussion on books, but I particularly like this James Whitten, Hastie and Tibshirani book, which is an introduction to statistical learning with applications in R, right? And this is available as a free PDF, or you can get it as a $25 not hard copy, but probably it's a soft copy. And then I've got what is going on at the moment in economics. Okay, and then finally, I said that there was this book, little cautionary tale. Oh, sorry. How big data increases weapons of math destruction. How big data increases inequality and threatens democracy. Okay, and the idea is that, you know, credit rating agencies have these algorithms to predict what is the probability of someone, I guess, not honouring their debts. Okay, it's fantastic at that. Is that the same thing as a good predictor of whether someone renting a house will make their monthly payment? Right? What happens if you want to rent a house? Don't want your credit score. Right? It's just very easy to misuse these things. Another one is they're very black box. Right? Who should decide whether someone goes on parole? Is it a judge? Or is it a model that spits out there's a 93% chance this person will commit a crime in the next year, right? Or who should, okay, anyway, I think I'm out of time, so okay, I'm done.